mm. So uh, welcome to the sixth class on statistical mechanics. And okay, hello. So this is the sixth class on statistical mechanics, and in the last few classes, we have been talking about the different ensembles. We started with thermodynamics, and then we talked about probability, and then from the probabilistic description, we started this very idea of ensemble. Okay, that there can be many microstates corresponding to a single macrostate, and then based on how your, what kind of system you are dealing with, okay, whether it's a open system or a closed system, based on that, your the thermodynamic variables that define the system would vary. Okay, so in some case, your temperature would be the right quantity to look at. Somewhere, energy will be okay. So based on what system we are talking about, we would have certain thermodynamic variables that give us the macroscopic description. And then there can be a microscopic description, and the link between the two comes from the statistical mechanics, where we talk about probability of different microstates corresponding to a single macrostate. And in the last two classes, we have first started with microcanonical ensemble, where we looked at the situation where energy remains constant. So it's like a closed system. Okay, energy and number of particles, all of them are constant. And then we moved on to canonical ensemble, where now you can exchange energy with the reservoir. So there the system is in thermal equilibrium with the reservoir. So what defines the system is now temperature, right? So that was the canonical ensemble. And today we would again move ahead with another ensemble called the macrocanonical or the grand canonical ensemble, where now we are talking about open systems where you can exchange both energy and number of particles. Okay. So in this case, you would now define your system in terms of temperature and chemical potential rather than number of particles and energy. Okay. So we would discuss about grand canonical ensemble, and what you would see is that there is a lot of similarity between, like, if you can solve for canonical ensemble, you can actually solve for grand canonical ensemble as well. So it's not very different. So all the questions typically that we have solved for canonical ensemble can actually be also, extended to grand canonical ensemble. Okay. Okay. So, and just to introduce myself, so I am a PhD student here at IISc, and this is something which we have to do as a part of its of the TA requirements for TMRF. And so here we go. Okay. So we would discuss certain basic concepts, and as we discuss, we'll solve some very standard problems as well in grand canonical ensemble, and see how and under what conditions the different ensembles actually give similar values. We'll also talk about that, and we would also discuss a little bit of Ising model, which is actually a very important concept in, a very interesting and useful model that can define a system of spins and how they interact and so on. So we would talk about that as well. And if there's any doubt, you can ask me. Okay. So macrocanonical ensemble. Now, in microcanonical, energy was constant. It was a closed system. For canonical ensemble, energy exchange was allowed. So in that case, temperature was constant. It's in thermal equilibrium. It was in thermal equilibrium with the reservoir. And now what happens if you have an open system? So now you can exchange both energy and number of particles, okay, with the surrounding. And So what you have is a microcanonical system where you define the system in terms of temperature, volume, and chemical potential, not number of particles. Okay, number of particles can change. So typically, this is how it would look like. So initially for canonical ensemble, you had a system and you had a heat reservoir and you could exchange energy between the two. Now you have a system and this region here, the surrounding is a heat, the spelling is wrong, heat bath. It will act as a heat bath as well as a particle reservoir. Okay, so that means what you can say is that the total energy can be written as ES, which is the energy of your system, plus ER, which is the energy of your reservoir, and together they give the total energy, which is constant. Okay, so the reservoir plus system, they as a whole act as a microcanonical ensemble. Okay, while the system individually, because it can exchange particle and energy, now becomes a microcanonical system. Okay, and again the total number of particles can be written as Ns plus Nr. Okay, so now if you consider that this particle reservoir of the heat bath is sufficiently large, okay, so in that case what you can consider is that you can write Es by E. Okay, and you can consider this to be much smaller than 1. Similarly, Ns by N can be considered to be much smaller than 1. So now what we can do is we can do a very similar process of what we have done in the canonical case. So in canonical case, you remember that you wanted to, so suppose we want to, what do you want to do? We want to find an expression for the probability density, right? And probability density is associated with the number of microstates. So in canonical ensemble, if you remember, we tried to find what is the number of microstate corresponding to the system being in energy state ES, right? And you said that that is same or you can say proportional to the condition where you say that the number, what is the number of microstates where your particle reservoir or the heat bath is in an energy E minus ES, right? So similarly, what you can now try to find is the probability P I Ns of finding the system in a microstate I with particle number Ns, and this would be proportional to omega R, that is, this is for the reservoir, where the reservoir has an energy E minus EI and the number of particles is N minus Ns. Okay, and in this limit where you have a large reservoir, you can actually do an expansion, and from there, so basically PIN is now proportional to this term. Okay, so you can now do an expansion. Basically, you need to find K ln omega R because you want to find the probability density. So from there, what you can do is you can do an expansion, and now you will have terms. So you can see this partial derivative coming in, and you're doing it once in terms of energy and then in terms of number of particles. Okay. Now, from thermodynamics, it's known that del S del E is 1 by T, del S del N is minus mu by T. So you can actually replace these terms here, and you would get an expression like this. Okay. So what you see is now you have an additional term which is coming up. So initially, in case of canonical ensemble, you only had this term, right? Now there is this additional term which is coming because now you can exchange the number of particles with the surrounding. Okay, so this is, so the probability of a particle of the system being in energy EI and with number of particles NS is proportional to this term. Okay, so if you now want to find an expression for the probability density, you would say that you try to normalize. Okay, and the normalization tells you that if you do a summation over all possible values of I and Ns, it should sum up to 1. So from there, you can actually normalize and get the normalized probability density, right? Now, again, this term here in the denominator is nothing but the macrocanonical or grand canonical partition function, okay? Similar to what we had for a canonical case. So if you have a system where the spectrum is continuous, in that case you can actually replace the summation by an integration. Okay, so this integration, you are having an integration over the phase space of this term e to the power minus beta h minus mu n, And then you have this h to the power 3n. And why is this coming? This is coming because of the uncertainty from the uncertainty principle, which says that the smallest volume that a microstate can occupy in the space is given as h to the power 3n. Okay. And then this n can take all possible values from 0 to infinity. So this is how it would look like. Okay. Now, if you are asked to So if you're asked to find the average energy or the average number of particles, so it's similar to what we have been discussing so far. So whenever you want to find the expectation value or the average of certain quantities, you actually, what do? Is you basically do a summation of the individual values of that quantity and their corresponding probabilities. Okay. So EI, and this is the probability of being in the state EI. Okay. And then summation over all such values. So similarly, for average number of particles, this is how you would find. So this is important because later we'll see that this description will very easily give us new ways of defining or estimating average energy or average number of particles directly from the partition functions. Okay. And the partition function is given by this denominator here. Okay. So here you have this additional term which is coming because of the macrocanonical end symbol. Now, if I ask you whether this expression is for distinguishable system or indistinguishable particles, will you be able to comment on this? Any idea? Just by looking at this expression of the partition function, can one say whether we are talking about distinguishable system or indistinguishable system? You can also write in the chat box if you have any comments, okay? And in case you have any doubt, you can also, stop me and ask. So this is something which we had discussed at the very start of, this ensemble theory, where you had a factor called Gibbs factor, if you remember, right? And the Gibbs factor is associated with this idea of whether the constituent, the particles are distinguishable or indistinguishable, right? So any idea? So see, if you have a distinguishable system, then you can, so if you have three distinguishable particles, so each rearrangement will give you a new arrangement, right? So that means you can rearrange them in, some n factorial ways, right? But if they're indistinguishable, then just by reversing or, interchanging their positions, we would not get a new state, right? It would not make any difference. So in that case, if you have indistinguishable particles, your number of microstates will reduce. So for indistinguishable system, you have a extra 1 by n factorial term coming in. Okay. Because you don't have this 1 by n factorial term here, which tells you that for this case, whatever we have written here, it's considering a distinguishable system. If you have an indistinguishable system, you have to add a 1 by n factorial here. Okay. Just be careful about this point. Okay. I hope it's clear. Now, once we know the partition function, or once we know the probability density, we can actually find the entropy, right? Which is nothing but the expectation value of minus KLN rho. Okay. And because we want to find the expectation value, that means you can actually write it explicitly as a integration like this, with n now varying from 0 to infinity, right? So what you have done here is you have so whenever you want to find expectation value, you are multiplying the probability density with this quantity minus KLN rho. and then you are doing a integration over the phase space. Okay. Now here you can explicitly write the expression for rho, which is given as k ln z plus k beta h minus k alpha n. Okay, this is coming from this expression, right? This expression here. Okay. So now once you have an expression for the entropy, what you can do is you can explicitly, make this, just simplify it further, which will tell you that if you consider this term here, right, the second term in this thing, that is nothing but, this integral is nothing but the average or the expectation value of your Hamiltonian, right? And similarly, when you have the same integral with the number of particles, it becomes the average number of particles. So basically you can now, simplify and write the entropy as k ln z plus k beta h, average energy, minus k alpha n. Okay, expectation value of n, your expectation value of Hamiltonian. So now what is important is you have now simplified the expression for S. Okay, here beta is 1 by kt, alpha is mu by kt. From here, what you can now do is basically you can consider this to be u. Okay, the expectation value of the Hamiltonian would give you the effective energy of your system. So you can write it as u, and then write beta and alpha as 1 by kt and mu by kt respectively. Take them to the left hand side, rearrange, and this is what you would get. Now at this stage you can understand it's similar to the expression of free energy that we had found in the case of canonical ensemble, right? So now this is another new potential which has come up for the macrocanonical case, which is again related to the partition function by this similar relation. Okay, so you can define this term as phi. Okay, so you can say that now phi is a potential which is related to the partition function by this relation. Okay, so once you know the partition function, that is the macrocanonical partition function, you can find phi, and once you have phi, you can define all the other thermodynamic variables from there. Okay, it's similar to f that we had found for the canonical case. Now, interesting point is you can actually simplify it much further. So what you can do is that phi is mu minus ts minus mu n, right? And you already know that energy U would be given as Ts minus Pv plus mu n. So what you can do is you can replace this term here, and what you would finally get is minus phi by kt is nothing but Pv by kt, which is equal to ln z. So this is a very useful relation for the macrocanonical ensemble, which, so you can very well see that once you know the partition function, this would give you the equation of state quite generally, and then it's a very important relation. It relates the different thermodynamic variables directly with the partition function. Okay, so remember this expression for the macrocanonical ensemble. Okay, and also remember how we got there. So now the partition function, this is how it looks like. Okay, alpha is mu by kt. So from here, what you can do is you can simplify it further. What you can do, you can write alpha as mu by kt. Okay, and you have an exponential here. So exponential of like e to the power alpha n, you can write it as e to the power alpha to the power n. Okay, and then you are doing a summation for n going from 0 to infinity, and you can see that the integral is over q and p, and only h out of these two terms, only h is a function of q and p. So basically you can consider this entire expression as a this expression here as the expression of the partition function for a canonical ensemble, right? And the extra term which involves n comes up because it's a macrocanonical ensemble. So now you have this term here. So if I change to, so you have this term here, which is the canonical partition function, okay, which is coming from this part because you are out of these two terms, only h is a function of q and p. So you can basically do this integral, consider this to be, that is nothing but the canonical partition function. And then e to the power alpha n can be written as e to the power mu by kt to the power n. And then you have a summation for n going from 0 to infinity. Okay. So what this is giving you? This is giving you a relation between the partition function for a macrocanonical ensemble with the partition function for a canonical ensemble. Okay. So this is the only additional term which comes in as a weight factor kind of thing. Okay. So the canonical partition function is nothing but a weighted sum of all canonical partition functions. Macrocanonical partition function is nothing but a weighted sum of all canonical partition functions, where the weight factor or weighting factor is given as mu e to the power mu by kt, called the fugacity. Okay. So what you can do? So now if you consider indistinguishable non-interacting particles, what would happen? You would have a 1 by n factorial term coming in, right? So then you can write the partition function for, and they are non-interacting. So you can write the partition function for n particles as partition function for one particle to the power n by n factorial, right? This is something we have discussed in the last two classes as well. Still, if you have any doubt, please feel free to ask, okay? So now, basically, because they are non-interacting, you can have individual probabilities are independent of each other. So you can write it as a product of all the individual probabilities, okay? And that's how you get to this expression. So now what you can do, you can write the grand canonical or the macrocanonical partition function as something like this. So you have replaced ZTVN by this expression. So what you get is a typical expansion of a exponential, right? So that means you can now replace this entire thing as exponential of e to the power mu by kt into z tv1. Okay. So this is how so once you know the canonical partition function for one particle, okay, if you have a system of n indistinguishable non-interacting particles, you can actually find the grand canonical or macrocanonical partition system from this relation. Okay. So if you consider our already known example of ideal gas, which we had solved for the canonical case, what do you see? So you see that the Hamiltonian is typically given as h equal to p square by 2m, right? And then you have suppose n such particles and it's in 3 dimensions. So your nu goes from 1 to 3n, okay? And you can actually consider that, you know, it's an indistinguishable system. So you can have this 1 by n factorial coming in. So you can have this 1 by n factorial coming in, and then you do try to find the partition function for the canonical case. Okay, first. So this is for the canonical partition function. This is how you define it. So you don't have any n yet. Okay. Now once this is something which we had already done in the last class, right? So what you do is basically you replace h by p square by 2m, and then it's a with some substitution, you get a very standard Gaussian integral, and you solve for all the values, and you have n such 3n such coordinates. So that means once you solve for one of them, you have to extend it to a power of 3n, and this is how it would look like. So this is the typical result that we have solved in the last class, which is the canonical case, okay, but canonical partition function. Now what you can do is you can also simplify it, and this is how it would look like. Now for the macrocanonical case, we know the relation that relates the canonical ensemble partition function with the macrocanonical partition function, right? So you would use that term here. So you can write that for so you can write ZTV1. This is the canonical partition function for one particle, which is given as V by lambda Q. And then the relation that we have derived just now, you can just use this expression to find the macrocanonical partition function. This is how it would look like, okay? So now once you know the macrocanonical partition function, you can find phi from there, okay? Phi is the potential. And once you get that, you can use all the standard relations which relate the, the different thermodynamic variables with like S, entropy, pressure, number of particles. So you can use this relations to actually define all the different thermodynamic variables. So this is how it would look like. Okay. So if you want to write pi as a differential, this is how it would look like. So this is the relation from where we have derived all these expressions, right? So this tells you that del pi del t is given as minus s, del pi del v is minus p, and then del phi del mu is minus n, right? So from here you can get all these expressions and you can try to derive for all the different thermodynamic variables. You can also find the equation of state from here. Okay. So till now what we have seen is that there are different ensembles and they can have different partition functions of similar form. Okay. So in the starting case with the microcanonical ensemble, you had G or mu omega, which is the number of particles, a number of microstates, and you relate it to entropy. So you write entropy as K ln omega or K ln G. And then for the canonical case, what you had is this canonical partition function, and minus KT ln Z was equated to the free energy. Okay. And for the macrocanonical case, you again have a new, like another, the grand canonical or macrocanonical partition function, and they have a similar relation with to another potential pi, which defines your system. Okay. So now an important point that so till now, this is what we have been discussing. Like we have discussed three different ensembles. Now, there are certain limits at which all these different ensembles would give you similar results. Okay. So now if you want to, actually see how, so in a system, if you have the average number of particles given as something like n, if you want to find what is the fluctuation about the mean, right? So suppose the same mean value you would also get from the canonical ensemble, right? So now when you have a macrocanonical ensemble, if you ask what is the, you know, the fluctuation about the mean, how do you define that? Okay. And that in a way would actually lead to the fact which would give us this limit where all these different ensembles become quite equivalent to each other. Okay. So this is your expression for the, so this is the expression for the macrocanonical partition function. Now, the point is we want to see how do we define fluctuations about the mean point. So basically, if you have a system, you have some mean value, you can have variance. So if the question here asks now if you can find the expression for the standard deviation, suppose, right? Because standard deviation will give you how much is the deviation from the mean, right? So if you want to find that, how do you do it? You have the information that this is how the canonical partition function looks like. Okay. Now what you can do is you can actually define the average number of particles. How do you define the average number of particles? So basically summation over all possible values, where you have all possible values of n and multiplied to it is the corresponding probability, right? So if you explicitly write it, this is how it would look like. Now, once you have this term, okay, can you, just by looking at it, can you say that suppose you have this expression, you know how Z looks like, and then this is your expression for n, the average number of particles. Can you find the relation between the two? Can you write this in terms of, maybe replace this average n expression in terms of the partition function Z? Any idea how to do it? Just by looking at it, what comes to your mind? How should we go from, use this expression to rewrite this term? Any idea? This is a very interesting and important step. I mean, you will have a lot of, such expressions coming up later. So that's why, do you know, any idea? So the idea is that, from here, what should you do so that you get a summation like this? So here you have an extra n term coming up, right? So from here, what should you do with z so that you get this uh, summation? That's the question. Even if you have any doubt, feel free to, just, ask, or should I, give some time? Are you thinking, or should I just, see, basically, you have to, if you want to go from here to here, if you want to get a n here, what should you do? You need to do a derivative of z with respect to mu, right? If you do a derivative with respect to mu, what will you get? Your n will be the coefficient which will come out, right? So that's the idea. Okay. So you can write it as del mu of kt ln z. Why ln z? Because you have a 1 by z here. You know that derivative of ln z, ln x is given as 1 by x, right? So that means this 1 by z tells you that you should have a ln z term here. And then you would finally have a del z del mu term as well, which would give you n, right? And this is nothing but, you already know that phi is given as minus kt ln z. So now you can write n, which is the average energy number of particles, as minus del phi del mu, right? See, this is the same thing that you got from here, right? Same relation. This n, okay, so that means what is this telling you? So the average expectation value of n, or the average number of particles for that macrocanonical potential, again equates to, the net n when you have a, thermodynamic description, where n is your total number of particles. So they are all related to each other, right? So this is how it looks like, right? So similarly, you can also do for average energy. Now this mean number of particle is identical to the thermodynamic particle number n, okay, which was equal to the fixed given particle number in the microcanonical ensemble. Right? So the deviations of the mean value in the macrocanonical ensemble are given by the standard deviation of the distributions. We want to find, so now we know the mean value. So now we know the mean n. We want to find the standard deviation of n. So what do you have to do for that? So you have to actually find the average. So this is the mean. You also have to find the second moment, basically, right? The variance has to be found. So what you do is basically you want this. You already know the expression for this. You have to find an expression for this. So if you explicitly write this expression, how will it look like? So basically, why am I discussing these questions this steps is because there can be numerous questions, but if you are well versed with, how do you write an expression for the different expectation values, how do you simplify the, this kind of expressions in terms of this differentials, then the solving of the questions will be much easier. It's this equations or this relations that are actually being used everywhere, right? So now you know the expression for the average number of particles. This is your expression for the variance, and from here, like, you can do a square root of this to find the standard deviation. That's the point. So now you want to find an expression for the average of n square, right? So how do you do it? So now you can understand that how will the average of n square look like explicitly? This is how it would look like, right? So you have n square here. That means you have to do a derivative twice, right? So, and then this is just to, so 1 by z, because you would need this, there's a 1 by z here, right? And then you have kt square, because if you do derivatives twice, you would have, so it's mu by kt kind of thing, right? You have beta here. So that would give you the kt term. And then del square z, del square del mu square of z. So basically a double derivative, right? So now what you can do is you can actually explicitly rewrite this term, rewrite this expression, okay? Rewrite this expression by using this relation, okay? That's too bad. So this expression can be rewritten by using this relation. So this is something which we get from this relation here, right? This is already derived. So you can do this substitution where now you replace kt del z del mu as z into the average energy, okay? So this is the expression that relates n square to n. And you can rewrite this, explicitly, like just do the derivative. So this is how it would look like. So now if you want to find the variance, you can just take this term to the left hand side. This is how it would look like. Okay. So this n is nothing but the thermodynamic particle number n, right? So you can write it as kt del n del mu at constant t and v. Okay. So this is your expression of sigma. Now what you can do, you need to find the sigma square. So you need to find sigma basically, right? And suppose you want to see how does it vary as a function of number of particles. Like all those are the questions that we want to address, right? So now this is a very important expression, okay, which talks about fluctuation in the microcanonical ensemble. So what is the variance of the number of particles, and how is it defined in terms of this, see, this is related to the temperature of the system, related to the derivative of the thermodynamic particle number with respect to the chemical potential, right? Now, at this point, we have to discuss a very important and interesting relation called the Gibbs-Duhem relation, okay, which actually is a relation like this. So it tells us that the different intensive variables like temperature, pressure, or the different chemical potentials, which are conjugate to the different extensive variables like S, V, or N, okay, they are not independent of each other. There's a relation between all of them, right? So there's a relation between all of them. So that means now if we look at our question at hand, you can write T mu is equal to small v dp minus small s dt. So where small v and small s are defined as v by n and s by n. Okay. So from here you can write that del mu del v at constant temperature is given as nu small v into del p del v at constant temperature, right? So this is the relation that you get for the one, you're just talking about one chemical potential, right? So you can basically just using this relation, you would get this, and from there you can write this expression. This is the Gibbs-Duhem relation. Why it is important? Let's see. So now we interpret T, V, and N as independent variables. The pressure is then a function of this variable. So basically, see, T, V, N, they are independent variables. Now pressure by itself is an intensive quantity, right? So that tells you that if now pressure is a function of T, V, and N, it should be of the form as something like V by N or N by V kind of form, right? Because it's an intensive quantity. So just by changing V, the pressure should not change, right? So that means you can write pressure as a form. I'm just losing my pointer. So you can write pressure consider pressure to have a form something like this. Okay, it's function of temperature and it's a function of V and N in this form. Okay, Now what you can do, you can actually try to rewrite the expression. So you can write del P del N, okay? And then what we're doing is basically, just doing derivatives. It's a typical derivative that we are trying to do here. So del P del V by N into del V by N by dN. So here you have considered N to be the variable, okay? So this is the form. This is the form that you would get. Okay, so this is del P del N. And this is how it looks like, okay? On the other hand, you can write, again, consider now V as your the variable, and then you can do the same. Okay, this is how it would again look like. So now based on this, you can actually use the Gibbs-Duhem relation, okay? And so you can see that, from these two equations, you get an expression like this, okay? And the Gibbs-Duhem relation gives you this term here. Okay, so this V by N is nothing but small v. So there is a similarity between these two terms, right? So you can write del mu del N is nothing but this term here. Why it is important? See, in the expression for sigma square, you had a term which involved del N del mu, right? If I go back, you had a term like this. But you can understand a derivative of N with respect to chemical potential is it's difficult to understand in terms of physical parameters, right? If we now want to, express this same expression, okay, but simplify this further in terms of some directly measurable quantity, how do we do that? So that's what we are trying to do. So now you know an expression for del mu del N, right? That's what we derive. So you can substitute that here. So basically what you would see is something like this. So now you can actually do the substitution and you're actually then writing it. So here now the compressibility comes up. Okay, so so now all these terms, T, V, K, these are all directly measurable quantities. Okay, so now you can actually write the expression of sigma square in terms of directly measurable quantities. And from there, you can actually find this ratio. So this ratio is basically a relation that actually gives you the idea about how the fluctuations are and how they vary with, as the size of the particle increases or as the number of particles increases, right? So you can see that it goes as 1 by root over V, right? So that means for large volumes, or if you want to relate V with N, that means for large N, gradually the relative fluctuations keep on decreasing, right? So what does it tell us? So physically, if you want to understand, this tells us that if you have a very large particle number or a very large system, then the deviations from the mean in the macrocanonical ensemble are vanishingly small. That means ideally you will be reaching towards the thermodynamic particle number itself. Okay, so whatever average or constant value of N that you had considered for the microcanonical case, your macrocanonical ensemble data will give similar or will tend towards that value in the thermodynamic limit where your number of particles are too large or the size of the system is very large. Okay, so that's where in the thermodynamic limit all the different ensembles become equivalent. Okay. Now, similarly, you can actually try to find fluctuations in energy as well. Okay. So how do you do it? So again, you can write the average or mean energy as something like this. Okay. So EI into P is the probability of being in the state EI and summation over all possible values. You can explicitly write the expression for the probability density as e to the power minus beta EI plus mu N by Z. Okay. And because now you have a EI here, you can understand in the last case you had a N here. So you did a derivative with respect to mu. Here you have the energy here. So you have to do a derivative with respect to beta, right? So this is how it would look like. So this is directly from the partition function, you can do this derivative to actually get the average energy. Okay. Now, you know that fugacity is given as e to the power mu by kt, right? So that means what you can now do is actually consider the fact that you can similarly use this relation to find E square as well. Okay. So here, this Z here is the fugacity. Okay. Now, E square. So again, you have to do double derivative with respect to beta. Okay. And then there's a 1 by Z, which comes from because of the ln term. So here you had single derivative is double derivative. Fine. So now you want to find the standard deviation about for the energy, right? So that means you can take this term to the left hand side and rewrite it. So this is how it would look like, right? It's similar to what we did for the particle number case, right? What's interesting is that now what you can do is you can write del sigma like sigma E squared by mu square. Okay. This is the average, this is like standard variance and the ratio of the two. And this is how it would look like. So what this tells you, basically you can actually rewrite it further and you would see that this tells us that whatever is the fluctuation in the canonical case, okay, the microcanonical case is always larger than that. So you have the canonical fluctuation and then there's this additional term which comes up and then which adds to the macrocanonical adds to the canonical to give us the macrocanonical fluctuation, right? And that is associated with the changes in like how things are changing with number of particles, right? So that means fluctuation in energy in macrocanonical case is always larger than canonical, okay? And what we saw is all ensembles, all this microcanonical, canonical, or microcanonical, all of them with large particle number, they yield same results. Okay, so this will also this term will also gradually decrease as you go to larger, system sizes or larger number of particles. Okay, so a quick recap is, let's try to just recap what we have discussed so far. It tells us that which expression shows the average energy within the canonical ensemble, right? So whenever you are trying to find average energy, you have to see that if the possible values of energies are EI, then the average is given as summation of EI with into the probability of being in the state EI, right? So based on that, one can answer what the answer will be. Okay. So for this case, the answer should be C, right? Because EI into e⁻ minus beta EI by Z is the corresponding probability. So this is how it could be. It's a typical definition for a canonical ensemble, right? Now consider the three collection of particles in microcanonical, canonical, and grand canonical ensemble. Which one physical property is constant in all the three ensembles? So that you have to consider that, so for canonical, microcanonical, you had a closed system. For canonical, you could exchange energy. For macrocanonical, you can, or grand canonical, you can exchange both energy and number of particles. So from there, you can answer this question. So obviously, total number of particles is not constant for the grand canonical case. Okay. Now, volume is a extensive quantity. So as you keep on, if your system sizes and all changes, and the volume would change, it's an extensive quantity. And then if you look at the typical thermodynamic variables that define the microcanonical or canonical or grand canonical ensemble, you would see that there is one quantity which there is a variable that defines all the three systems, and that remains constant for all the three cases. Okay. So for this case, the thing will be like temperature. You can understand that for canonical case also it's constant, for grand canonical case also it's constant. Microcanonical system, there's no exchange of energy, so in that case also. So so this tells us that for if you want to look at a physical quantity that remains constant throughout all the different ensembles, you can consider energy to be, temperature to be 1. Okay. So now let us, so we did solve for ideal gas, right? So if you want to do a similar kind of thing for an ultra-relativistic gas. So for ultra-relativistic gas, I've already solved in the canonical ensemble how the partition function and all of that looks like, right? Now you have to extend the same further a little bit and see how you already know the partition function for the canonical case. You have to write the partition function for the macrocanonical case. So you know that it's nothing but a weight sum, right, with the fugacity. So that's what you have to do. Okay. And then you can try to find the different thermodynamic properties for n relativistic gas molecules. Okay. So the typical Hamiltonian looks like this. Okay. That means now you can first try to find the canonical partition function, which is nothing but this term here. It's something which we have already discussed many times now, till now. And now what you can do is, so you can see that your Hamiltonian is only function of momentum. That means you can take the d3 and q out of the integral, and this is the integral that you have to do. At this point, what should we be doing? So if you remember, we have this, see, the what do I say? The magnitude of P comes up here, right? So this tells us what should be done, right? So that means if you have to explicitly write it in the Cartesian coordinate, it would be like something like square root of px square plus py square plus pz square, right? So from there, if you remember, what we saw is because you have the magnitude involved here, you can actually, go to a spherical coordinate system where you can consider a sphere whose radius is given as p nu, right? So you can go to spherical polar coordinates, and then you have an integration from 0 to infinity, 4 pi p squared dp, and e to the power minus beta cp. Okay. And then you have n such integrals, so to the power n. Okay. Now this is a typical expression of gamma function. So you can write it as gamma 3. Okay. So this is now z tvn would be given by this relation here. So this is something which we had already derived in the last class. Okay. So this is the canonical partition function. Now for the grand canonical case, what you can do is you can use this relation here. This is something which we just derived, right? So you can write it as exponential of exponential mu by kt into z tv1. So z tv1 is the canonical partition function for one particle. Okay. So if you put here n equal to 1, this is your expression of z tv1. So that gives you the expression of z tv mu. Whenever you have mu here, understand that it's a macrocanonical ensemble that you're talking about. Okay. For canonical ensemble, you would have n. Okay. So now this is the expression of z. Now, once you have z, what can you do? You can try to find phi, right? And similarly, once you know phi, you can find all the different thermodynamic variables. Okay. Now for n harmonic oscillators, okay, how to do this? So it's a similar process. It's something which we have already solved for the canonical case. So here, what you have to do is basically this is how your Hamiltonian would look like, right? Okay. So now using this expression of the Hamiltonian, you can actually try to here, and like for some particular n, consider a canonical partition function. This is how it will look like. And then you have to relax the fact that your n can now also vary, and then it becomes a macrocanonical ensemble, right? So this is for the canonical ensemble. So you can try to solve it. So you would get two such Gaussian integrals with some substitutions. And this is the expression for the canonical partition function. From here, you can also find the free energy, which is minus kT ln z, right? But what you have to now do is you have to write the macrocanonical partition function, right? So that means you have to now relax the fact that your n can also vary. Whenever you have partition function, your n is constant. You're only exchanging energy and n is constant. So this is for a particular n. This is the partition function for the canonical ensemble. Now your n can vary from n equal to 0 to infinity. It can take all different values. Okay. So then you're writing the partition function in terms of t, v, and mu. So this is your macrocanonical partition function. Okay. This is the relation. So you can just substitute the expression that you have here, kt by h cut omega to the power n. You can substitute here. That will be your expression for the grand canonical or macrocanonical partition function. Okay. So this is how it would look like. So now, so this was about, grand canonical partition function. So basically, whatever you had initially done for canonical partition function, we did solve different kinds of questions, right? We also solved about cases where you have different energy states and you have a discrete energy level. So you could also define the partition function in those cases and try to find the different thermodynamic variables. So we did solve different questions for canonical ensemble. Okay. Now, all those examples can also be taken up for the macrocanonical ensemble. Only the would actually make the difference, right? So once you know the expression for the canonical partition function, you can actually find the expression for the macrocanonical partition function and therefore define phi and all the other thermodynamic variables. Okay. So the main point is, if you can solve for canonical ensemble, you can also solve for macrocanonical. Like you can just have a practice of solving for canonical part. Macrocanonical will be very similar to that. Only this additional steps would come up. That is because of the fact that now you can exchange n, like your n is no longer constant. Okay. Okay. Now you briefly talk about an important aspect, which is the Ising model, and you see that it's a very interesting model, useful model, which talks about, so if you have a collection of spins, okay, and suppose if you apply a magnetic field, so the spin will try to align in the direction of the field. But then based on how the spins are aligned with each other, there will also be exchange energies and there will also be interactions with each other. Okay. So if you look at nearest neighbored interactions, okay, how do you typically define a Hamiltonian? And from there, you would get a model that will tell you, okay, that will give you a description of, maybe ferromagnetism or antiferromagnetism. Like you can also define all these different kinds of, properties of material from this model. Okay. So in this model, what you consider is like we would first look at a very simple case where you have n atoms in the presence of z-directed magnetic field H. Okay, and these are spin half particles, so you can have plus half or minus half. Okay, that's the idea. And so you apply a field in the plus z direction. So now your spins would try to align in the direction of the field, right? So there will be an alignment, and that will be associated with some energy, which would be given as this term here. Right? So this term here, minus mu H. So this term here, this is coming from the fact that all these different atoms with different spins, they would try to align to the external field. Okay. And then they would also interact with each other. Okay. So if there are two spins close by, they would also try to align with each other. There'll be an interaction. So that is given by the first term here. So here we have considered that, we do a summation over the nearest neighbor. Okay. Considering that only the nearest neighbors interact. Okay. Now, this J here is called the exchange energy. Okay, mu is the atomic magnetic moment. So here exchange energy, you can consider that for ferromagnetism, your J will be a positive quantity. For antiferromagnetism, negative. So here, so if J is positive, you can understand that when Si and Sj are aligned to each other, you have minus J into a positive quantity. So that means the energies will be lower, right? So that means it's energetically favorable that if you have two spins close by, it's favorable that they try to align. Okay. Now, suppose if they are not aligned, then you would have your energies would increase, right? So this term is associated with the exchange energy, and then you have here the interaction, alignment to the external field. Now, the first thing that one can do is a typical mean field approximation. What do you do here? So you consider that all the spins are seeing a similar kind of field, okay, and That similar kind of field can be some effective H. Okay. So, and then there's a average spin for all of the cases. Okay. So that's the mean field approximation. So what you can now consider is you can write the energy of ith atom. Okay. And that is given as my pointer goes. So you can write the energy of the ith atom as minus j by 2. Okay. So k goes from 1 to z. Okay. So this is your exchange term, and then you have the alignment term, right? So what you can basically do is a half factor is added here so that you don't count, the pairs 2 times. Okay. And the total energy would be then given as summation over I EI. Okay. So this is the energy of the ith atom, and summation over all such atoms would give you the total energy. Okay. Now, what you can do is you can rewrite this energy of ith atom. Okay, this expression of energy of ith atom as something like minus mu H effective SI, where H effective actually has two components. One is the external field H, and another is the internal field, which comes from charge. So there are two terms here. One is the external field, another is the internal field generated by neighboring atoms. Okay, so this is the effective H that each of the schemes see. Okay, and then what you can consider is you can consider a single atom in some effective field HM. Okay, and from Boltzmann distribution, we can actually try to find the mean spin of the atom. How do you find mean? So always, whenever you're finding mean or expectation value or all of this, what do? You take the individual values and multiply by the product, by the probability of being in that value, and sum over all possible values. That would give you the mean, right? So that's what is being done here. So there are two possible values of the spin, right? Plus, it can be plus or minus. Okay. And then each of them is associated with an energy of minus mu m and plus mu m, minus mu h and plus mu h. Okay. So from there, you can actually find an expression for the mean spin of the atom. So this is how the mean spin looks like. So now what you can consider is you can consider that all atoms have identical spin, which is given as the mean spin. Okay. And all of them see a effective field, which is given as H effective. Okay. So that means this is how the expression will look like. Okay. Where S is given by this relation here. So whenever you're writing H, so as you can see, now you have substituted this term, right? Replacing HM by H effective. So from here, you can actually try to define certain critical, parameters like critical temperature or critical magnetic field, and why they are like physically useful, we'll understand as we proceed. But so now you have a expression for TC or HC. So basically, you can actually rewrite the expression in terms of these terms. So you can write the mean S as tan hyperbolic of this term here. Okay. Now, once you know the expression for the mean S, you can actually find the moment, magnetization. Okay, the net magnetization. So then you are multiplying by the moment, and this is your mean spin into n. Okay, so this is how it would look like. So that means now from here you can actually get a measure of the effective magnetization of your system, right? Now the point is that if you go by this method, you would get a plot something like this. So this is how the plot will look like when B is 0. This is the case when B is not equal to 0. So what this is telling you is that when B is equal to 0, so if you consider this case first, so you would see that there beyond a certain temperature, there is no magnetization. Below the temperature, there is a magnetization. So there is some kind of a critical temperature where a phase transition is happening. Okay. While in the second case, there is no such transition. However, if you fix the temperature, okay, and change the magnetic field from plus to minus, you would see a discontinuous change in the magnetization value. Okay. Now, what we'll see is that this mean field approximation is by which we had reached to this point is actually not always true. Okay. When will it be true? So see, you're doing an approximation where you're considering that each spin has some mean spin and each spin is seeing the same field. Okay. So this will be true when you have a large or a bigger system where there are many uh, neighbors, right? However, if it is a one-dimensional small system where the number of neighbors are limited, in that case, obviously, different spins will see different things. If the boundary, if it is a very small system, then obviously the systems at the boundary will be very different from how they are at the center. So all these issues would come up. So that means for smaller dimensions, what happens is that the mean field approximation does not hold always. Okay. And this is also, you can understand it's something to think about, right? You are finding a temperature below which it's magnet, and there is no external magnetic field, but you find a critical temperature where below that it has a magnetization. Just above that, there is no magnetization. Okay, so that's also something to think about. So the problem with mean field model is that it assumes that all atoms are situated in identical environments, which is not actually true. And hence, if the exchange effect is not sufficiently large to cause global alignment of the atomic spins, then there is no alignment at all, right? This is what happens when you do the mean field approximation. But you can understand that normally what happens is if the temperature exceeds the critical temperature, the global alignment disappears. But the local alignment is still there. Okay, so clumps are still there. So the mean field by itself is not sufficient. Okay. So if we actually don't do any approximation and try to solve this thing explicitly, maybe we start with one dimension, what do we get, right? So here what we have done is we have again considered the same system, but now in one dimension, okay? And you have n such spins. You have taken all this, combinations. So this is the exchange term, and this is the, this the alignment term, and here you have made it symmetric by writing it in this form. Okay, so now what you can do is you can define a partition function. If this is the energy, okay, how do you define a partition function? So your si and si plus 1, all of them can take values, plus 1 or minus, right? And then your number of particle ranges from 1 to n. Okay, so that means this is how the partition function would look like. Okay, here we are not doing any uh, approximation yet. We are just writing how things are without any approximation, right? So what you can now do is you can actually try to write z. This is how the partition function looks like, right? So you can try to simplify it by trying to write how this term would turn up. So if you have a 2 x 2 matrix which talks about this interaction between a pair, okay, these terms would define the matrix elements, right? So you can define a matrix like that. This is an exact solution, remember. Okay. So you define this matrix like this. So Si is one spin which can take plus minus one value. Si plus 1 is another spin which can also take plus minus one value. And they interact by this transfer matrix, which is given by this relation here. Basically, you're rewriting this form as a 2 x 2 matrix. So now you have, this is for two spins. So you have n spins. Okay, so you have to do a summation over all the spins and all the product, lattice sites as well. So what you do is basically you do a trace of all these quantities. And that is nothing but trace of t to the power n. So that means once you know the transfer matrix, you can actually find the partition function directly from here. Okay. So the traces arise because we have imposed periodic boundary conditions. Okay. And that means if we can solve for the trace of t, you can solve for trace of t to the power n as well, right? Now to solve for trace of t, what you can do is you can diagonalize this matrix. That would give you the eigenvalues of t, right? And that turns out to be lambda plus minus. Okay, so lambda plus is a eigenvalue, lambda minus is another eigenvalue. Okay, now the partition function is then written as z plus to the power n plus z minus to the power n, right? So you can understand because why? Because you have t to the power n, you have t to the power n here, right? So once you find the eigenvalues of t, that to the power n would be the different eigenvalues of uh, t to the power n, okay? And then you have to take a trace, that means you have to do a summation. So z becomes lambda plus to the power n plus lambda minus to the power n. And then you can do these adjustments to approximate this value to the larger root. So lambda plus is greater than lambda minus. So you can lambda plus to the power n is approximately the partition function. Now, once you know the partition function, so what you can do is basically now from the partition function, you can define a magnetization. Okay. So this is how the magnetization would be defined. Okay. And this turns out to be 0. So what we see is that the true physics for D equal to 1, which is the one-dimensional case, is very different from that suggested by mean field approximation. So here, when B is 0, there is no magnetization. Okay. While in the other case, when we had done for the mean field approximation, there what we were seeing is below a certain temperature, even at 0 field, there was a magnetization, right? But when we solve it explicitly, like, uh, with the exact solution, that shows that when B is 0, there is no magnetization. While the J term in the energy encounters or encourages the spin to align, it is completely overwhelmed by thermal fluctuation for any value of temperature. So that means what this is telling you is that thermal fluctuations always win in one-dimensional systems. Okay, they never exhibit ordered phases, and for this reason, never exhibit phase transitions. So the mean field approximation is bad for one dimensions. Okay. This is something to remember. So the mean field approximation can give better results when you have higher dimensions where the number of neighbors are more. Okay. So each spin can effectively be approximated as the mean spin, the one that we were doing previously. That works at higher dimensions. So now based on this, we try to solve some questions. Now, you have to understand that this is a very useful and important topic to study. Okay, so if even from the exam point of view, in almost all competitions or all examinations, you have some question from the Ising model. Okay, so just be at least have a basic idea of how to go ahead with this. Now, this is a question. It says that consider a one-dimensional Ising model with n spins at low temperature where almost all spins are aligned parallel to each other. Now, there'll be a certain spin flips, and each of them will cost an energy of 2J. Okay. Now, if there are R spin flips, the energy of the system would be given as minus Nj, which is just for the initial case when things are aligned, and then plus 2Rj. The energies keep on rising when you have flips. Okay. And how can you achieve the number of flips? That is nothing but NCR. Okay. Now, based on this, can you try to find the partition function? Okay. How to do this? I'll give you a couple of minutes maybe. So whenever you are seeing the video, just try to solve it first. So see, like first consider the case that if you're really talking about, energy levels, these are discrete energy levels. You want to find partition function. You can, to simplify, you can first choose a pair. So if you have two spins, okay, and what are the different possibilities? And each of the possibilities would give rise to certain energy, right? So what are the different energy states and the different probabilities of getting those different energy states? If you can solve it for two particles, then you can two spins, then you can extend it to n spins. Okay. So if you consider, the three energy levels, okay, so you consider that what can happen. So your R, if your R is, it can be, there can be a flip, there cannot, might not be a flip, right? So the possible values would be like, so just consider three cases. What are the three cases? So first is R is equal to 0. So if you put R equal to 0, you get a minus 2j. Okay, so there is no flip. Then you have the case where you have R equal to 1. Then what happens? They cancel out, so you get E1 equal to 0. Similarly, then now you have, uh, if R is 2, then you would have a 2j. So that means this is how it would look like for, for this three states, energy states. If you want to find the partition function, this is how it would look like, right? So here you have, so e to the power, this 2j can happen, minus 2j can happen in only one way. 2j can also happen in only one way, but 0 can happen in two ways. Either it can be, you know, up, down or down, up, right? So that's why you have a 2 here. Okay. So this is for this states. Now, what you can do is, this is how it looks like. Now, if you have n such cases, you have to just consider that they're independent events. So that means you can have to the power n. Okay. So this is how it would be. Right. So the answer should be this. Okay. So this is another question which says that consider a system of two Ising spins, S1 and S2, and taking values plus minus 1 with interaction energies given as this term here, minus j S1 S2. Now for large T, the average energy of the system varies as C by kBT, where C is given as what? That means you have to first find an expression for the average energy. Right? You have two spins. So first point is, if you have two spins and each of them can take plus or minus 1 values, what are the different energy states? What is the probability of each energy state, of being in each energy state, right? So if you know the energy values and if you know the probability of being in those energy values, that means you know the expression for average energy, right? And then put the limit of, large T. That would give you the answer. Okay. Just like whenever you guys see the video, just try to solve it, like try to work it out. make a table, okay? Make a table of S1, S2, the different values, the different energy states, and the probabilities. So see, basically what you can do is it can be both one, 1 + 1 or -1, and two such options, and then both minus, right? So now it's similar to the question that we have initially solved, right? So what can you do? You can try to write an expression for the average energy. Okay, the individual energy values. This is the, you can consider it as a degeneracy, like what are the different possible ways, okay, that gives the same energy. And then this is the probability term, right? So that means -2 j into e to the power j by kBt plus 2j into e to the power minus j by kBt divided by this term here. So this is again the partition function. Now once you have this expression, now you can actually, so you have a j by kt kind of term, right? So here you can use the large T limit. Basically do an expansion of these terms and use the large T limit. So this is how it would look like. You can simplify it further and you would get C as minus J square. Okay, so most of these questions that we are discussing now has come in different competitive exams, and similar questions keep coming. So the Ising model is a topic that is often there whenever you are going for any exams. Okay. Okay, now this is another question which says that now consider a system with three spins. They can also take +1 or -1 values. The energy of the system is given, and this is how it is defined. Okay, where J is positive, the minimum energy and the corresponding number of spin configurations are. This is comparatively simple. So you have to again look at what are the different possible values of S1, S2, S3, and the different combinations, and what are the different energy values that they give. You have to look for the minimum value and see in how many ways can you get that. Okay. So you can understand that typically, the spins always try to, align in the same direction. So now if you consider S as all of them as +1, this is how the energy would look like, right? Similarly, you can also have a state where all of them are -1, right? And that will also give you the same energy. And as you can understand, this should correspond to the minimum energy state because that's the most favorable configuration, right? So this can be achieved by two ways, right? So that's already telling you that the answer should be C, right? So yeah, so these are very straightforward examples and or questions, but they keep coming. So just be used to this very idea. Just remember that there's this model that can be used to define. And now we are talking of very simple things, but this can be extended. So we just did for one dimensions, but you can actually like there are different questions that can come up with higher dimensions as well, and how the phase transitions can be looked at from directly from the Hamiltonian, just how as we did, but in higher dimensions also we can actually work with the Ising model and see how things turn out. Okay, and at higher dimensions the mean field approximations gradually become better. The maximum energy, if you see, would be when things are misaligned, and that would be given as equal to J. So now you consider three Ising spins at the vertices of the triangle, okay, and they interact with each other. There's a ferromagnetic Ising interaction, so they try to align in the same direction, and J is a positive quantity in that sense. And now the partition function of the system is given as what? Okay, so now you have to look at all possible energy values and the corresponding moment probabilities, and from there define the partition function. Okay. So again here, if you just explicitly write the Hamiltonian and look at all the different possible combinations, okay, so you get 3J and minus J. These are the two energy states. And what is the degeneracy? How can you achieve this state? So you can have, there are two ways of getting 3J and there are six ways of getting minus J, right? So that already tells you what the partition function should be, right? 2 into e to the power minus 3 beta j plus 6 into e to the power beta j. That's the basic definition. Just directly, once you know the energy states and the possible ways, it's the summation of all the like e to the power uh, beta h or beta e terms, right? So the answer would be A, not A, B. Yeah. Be careful about the signs, okay? Minus j and 3j. And it's e to the power minus beta e, okay? Just be careful about it. Okay, now there's another question which says that now the Hamiltonian again has this three spins, plus minus one are the different values. H is given. You have to find the average energy. Okay, this is something similar to what we have already discussed so far. So we can try to, give it a try. So you can just actually, look at all the possible combinations. Okay. This is how it would look like. So now you have to first find, so you can directly, look at what are the different energy values and what is the probability of getting to that energy value, right? So in how many ways can you go? And so that number of ways divided by the total possible combinations would give you the respective probabilities, and then multiplying the probabilities with the energy state would actually give you the average energy. Okay. So here you have three energy states, either minus 2J, 2J, or 0. And they can have degeneracies as 2, 2, and 4, right? So that means the probability of being in minus 2J state is given as 2 by 8. Okay, again, this is 2 by 8, and this is 4 by 8, right? So you can just, this is how you can write it. So EI into GI here actually takes into account the degeneracy, okay? E to the power minus beta EI by Z. So this is your Z. So, and then you can simplify it further. Be careful about this, like just be used to, this substitutions of where to use hyperbolic, what are the different expressions and all that. And basically this term is the cosine. Okay, this is the expression for sine hyperbolic. And then once you substitute that, this is the average energy that you get. Very straightforward questions based on the same concept that we have been discussing. Okay. So thank you. So today we did discuss about macrocanonical ensemble, and it's actually an extension from the canonical ensemble. So in a way, if you can solve for canonical ensemble, you can also solve for macrocanonical. It's just a weighted sum where the fugacity term comes in. Okay. And we did discuss about fluctuations in macrocanonical ensemble, which takes into account, or brings to the fact that if you go to much larger systems or in thermodynamic limit where n is sufficiently large, then all the different ensembles give us same results. And then we actually discussed about Ising model, which is also a very important model that can be used to define system of spins and how they can interact with each other and with an external field. Okay, how do you define magnetization from there? How can you get the partition function there, and then from there define the magnetization? And we did solve for 1D, and we saw that the mean field approximation does not hold that good at lower dimensions. But the typical way of solving for mean field approximation was something that we discussed. And then it can also be extended to higher dimensions as well. Okay. So that was about today's class. Uh, Thank you.